Why can't anything go faster than light? I mean, really, what's stopping you? You've got a rocket, you keep adding fuel, you keep accelerating. Shouldn't you just keep getting faster and faster forever? Well, here's the thing. The universe has built-in speed limit, and it's not arbitrary. It's woven into the very fabric of space and time itself. Welcome to the channel. I'm so glad you're here because today we're going to crack open one of the deepest mysteries in physics. And by the end, you'll understand not just that nothing can outrun light, but why the universe absolutely forbids it. Stick around till the end. This is one of those ideas that completely changes how you see reality. And if you love exploring physics with clarity and wonder, hit that subscribe button. Let's figure this out together. All right, let's start with something that seems almost too simple to bother with. What is speed? You might say, well, that's easy. Speed is how fast something's going. And sure, that sounds right, but let me ask you this. Fast compared to what? See, here's the thing. If you're sitting in your chair right now, you'd say you're not moving, you're at rest. But hold on, the Earth is spinning. So relative to the center of the Earth, you're actually whipping around at about 1,000 miles per hour. And the Earth itself, it's orbiting the sun at something like 67,000 miles per hour. And the sun is moving through the galaxy, and the galaxy is moving through space. So are you moving or not? The answer is, it depends on who's asking. This is what we mean by relative motion. Speed isn't some absolute thing stamped onto an object like a price tag. It's always measured relative to something else. When you say a car is going 60 miles per hour, what you really mean is 60 miles per hour relative to the road. Relative to a bird flying overhead, the car might be doing 50. Relative to a passenger inside, it's doing 0. Now here's where it gets interesting. Let's say you're on a train moving at 50 miles per hour. And you throw a ball forward at 10 miles per hour. How fast is the ball going? Well, if I'm standing on the platform watching, I'd say the ball is moving at 60 miles per hour because I just add the two speeds together. That seems perfectly reasonable, right? Speeds add. You're moving. The ball's moving relative to you, so I just combine them. And for everyday stuff, cars, trains, baseballs, that's exactly what happens. Speeds add up in a nice, sensible, Newtonian way. But now let me ask you something a little strange. What if instead of throwing a ball, you turn on a flashlight? The light leaves the flashlight at, well, the speed of light. Let's call that c, about 186,000 miles per second. So here's the question. If the train is moving at 50 miles per hour and the light is moving at c relative to the train, then relative to me standing on the platform, the light should be moving at c plus 50 miles per hour, right? Just like the ball? Wrong. This is where the universe does something deeply weird. It turns out that everyone, you on the train, me on the platform, someone in a rocket ship flying by at half the speed of light, we all measure the speed of that light beam to be exactly the same value. C, not c plus a little extra, not c minus something, just c. Light doesn't care how fast you're moving. It always moves at the same speed relative to you. Now that sounds crazy. It sounds like it violates everything we just said about adding speeds. And you're right, it does violate our everyday intuition, but it doesn't violate the universe. The universe is actually telling us something profound here. Our intuition about how speeds add is only approximately true. It works fine for trains and balls, but it breaks down when you get close to the speed of light. And that strange fact, that light speed is the same for everyone, is the key to everything. It's the crack in the wall that, when you follow it, brings the whole structure of space and time tumbling down and rebuilds it into something far more beautiful. Okay, so we've established that the speed of light is the same for everyone. Now let's talk about mass, because mass is about to do something very strange. You probably think of mass as just the amount of stuff in an object. A bowling ball has more mass than a tennis ball. Simple enough. And if you want to get something moving, the more massive it is, the harder you have to push. That's Newton's second law. Force equals mass times acceleration. More mass means you need more force to get the same acceleration. Now here's a thought experiment. Let's say you've got a rocket ship out in space, far away from any planets or stars. You fire the engine, the rocket accelerates. You fire it again, accelerates more. You keep firing the engine, adding energy, and the rocket keeps speeding up. In Newton's world, this could go on forever. There's nothing stopping you. Keep adding energy, keep accelerating, and eventually you'd go faster than light. Why not? But remember what we just learned. Light speed is the same for everyone. That's a law of the universe. So something has to stop you from catching up to light. But what? Here's where it gets beautiful. It turns out that as you go faster, your mass increases. Now hold on, I don't mean you're accumulating more atoms or picking up space dust. I mean the mass itself, the resistance to acceleration, actually grows. The faster you're moving, the harder it becomes to accelerate you further. Let me put it this way. At everyday speeds, walking, driving, even flying in a jet, the effect is tiny, unmeasurably small. But as you approach the speed of light, something dramatic happens. Your mass starts climbing. Not just a little, it climbs steeply, rapidly, without limit. By the time you're at 90% the speed of light, your mass has roughly doubled. At 99%, it's about 7 times larger. At 99.9%, it's over 20 times larger. And as you get closer and closer to the speed of light, your mass grows toward infinity. Think about what that means. If your mass is growing and you're trying to accelerate, you need more and more force to produce less and less acceleration. It's like pushing a car. Easy at first, but imagine if the car kept getting heavier with every inch it moved. Eventually, you'd need infinite force just to budge it. That's exactly what happens. To actually reach the speed of light, you'd need infinite energy, and the universe doesn't have infinite energy lying around. Now here's the deepest part. This isn't a practical limitation like we don't have a strong enough engine. It's a fundamental law. The speed of light isn't just fast. It's a barrier built into the structure of reality itself. And here's the kicker. This increasing mass, it's not really about mass at all. It's about energy. Einstein showed us that mass and energy are two sides of the same coin. That famous E equals mc squared. When you add energy to something to speed it up, you're not just making it go faster, you're increasing its mass energy. And that mass energy resists further acceleration. So the universe has this beautiful self-consistency. The faster you go, the more energy you carry, the harder it is to go faster still. And light sits at the boundary, the ultimate speed limit, unreachable by anything with mass. It's not that the universe is trying to stop you. It's that the rules of the game make going faster than light logically impossible. Like asking what's north of the North Pole. All right, let's dig into what actually happens when you try to speed something up, because this is where the rubber meets the road, or rather, where the rocket meets the cosmic speed limit. Imagine you're pushing a shopping cart. You give it a shove, it speeds up. You give it another shove, it speeds up more. Every push adds energy, and that energy goes into making the cart move faster. Simple, right? Now let's do the same thing with our rocket ship. You fire the engine. Boom! You speed up. Fire it again. Faster still. And here's the question. If you keep adding the same amount of energy with each burn, do you keep getting the same increase in speed? At low speeds, yes. Double the energy, roughly double the speed. Everything behaves nicely. But as you approach the speed of light, something strange happens. You fire the engine, add the same amount of energy as before, but you don't speed up as much. Fire it again. Even less speed gain. Keep going, and you're dumping in enormous amounts of energy for smaller and smaller increases in velocity. It's like running through water. At first, you're jogging through a puddle, easy. Then you're waist deep, harder. Then neck deep, exhausting. And finally, you're trying to run through concrete. Here's why. Energy doesn't just go into speed, it goes into momentum. And momentum is mass times velocity. But remember, as you speed up, your mass increases. So when you add energy, some of it goes into increasing your speed, but more and more of it goes into increasing your mass. Let me give you some numbers to make this concrete. Say you're at 50% the speed of light and you add enough energy to increase your speed by 10%. Fine. But now you're at 60% and your mass is noticeably higher. Add the same amount of energy again. You might only gain 8% more speed. Do it again at 70%, maybe 6%, at 90%, maybe 2%. And here's the brutal part. As you approach the speed of light, your mass approaches infinity. That means adding any amount of energy, 1 trillion joules, a quadrillion, the entire energy output of the sun produces less and less speed increase. The closer you get, the more energy you need for tinier and tinier gains. Eventually, you hit a wall, not a physical wall, a mathematical one. To actually reach the speed of light, you'd need infinite energy, not just a lot, not just more than exists, infinite. And infinity isn't a number you can reach by adding things up. So here's what the universe is telling us. Light travels at c because light has no mass. Photons can live at that speed. But anything with mass, electrons, atoms, rocket ships, can only approach it asymptotically, forever getting closer but never arriving. It's like Achilles chasing the tortoise in Zeno's paradox, except this time the paradox is real. You can get to 99% of the speed of light, 99.9%, 999.99999%, but never 100%. And this isn't an engineering problem. It's not about building a better rocket. It's baked into the mathematics of energy and momentum in a relativistic universe. The speed of light isn't just the speed of light, it's the speed of causality itself, the maximum rate at which cause and effect can propagate through the universe. And nothing with mass can ever reach it, because the universe won't let you carry enough energy to get there. That's not a limitation. That's the rule that makes everything else work. Now, I want to make something absolutely clear. The constancy of the speed of light isn't a theory we cooked up because it sounded nice. It's an experimental fact. Nature told us this, and we had to listen. Let me take you back to 1887. Two guys, Michelson and Morley, did one of the most important experiments in the history of physics. They were trying to measure something called the ether, this invisible stuff that scientists thought filled all of space. The medium that light waves traveled through, like sound travels through air. Here was their reasoning. Earth is moving through space, right? So we're moving through this ether. That means light should travel at different speeds depending on which direction you measure it. Just like if you're swimming in a river, you move faster downstream than upstream. They built this incredibly sensitive device to measure the difference. And you know what they found? Nothing. No difference. Zero. Light traveled at exactly the same speed in every direction, no matter how the Earth was moving. It was as if the river wasn't there at all. This result baffled everyone. They repeated the experiment. They improved it. Other people tried it. Same result every time. The speed of light was always the same, regardless of the motion of the source or the observer. Now this is weird. Think about it with sound. If I'm standing still and a train is rushing toward me blowing its horn, the sound waves get compressed. That's why the pitch sounds higher. The speed of the sound relative to me changes depending on whether the train is coming or going. But light doesn't do that. If a spaceship is racing toward you at half the speed of light and turns on a headlight, that light doesn't come at you at 1.5 times the speed of light. It comes at you at exactly c, the same speed you'd measure if the ship were sitting still. This is so contrary to everyday experience that even Einstein struggled with it at first. But once he accepted it, really accepted it as a fundamental fact about nature, everything else fell into place. He realized if light speed is always the same for everyone, then something else has to give. And that something is space and time themselves. See, we assumed space and time were absolute, that a meter is a meter and a second is a second for everyone, everywhere. But if light speed is constant and speed is distance divided by time, then distance and time must be flexible. They have to stretch and squeeze to keep light speed the same for all observers. Two people moving relative to each other literally experience time at different rates. They measure distances differently. Your now and my now aren't the same if we're in relative motion. Space and time aren't the rigid stage on which physics happens. They're part of the performance itself. And here's the beautiful part. Every prediction that comes from taking this seriously, time dilation, length contraction, mass energy equivalence, has been tested thousands of times. Particle accelerators, GPS satellites, cosmic ray observations, atomic clocks on airplanes. Every single test confirms it. The speed of light being constant isn't something we chose. It's something nature insists on. And once you accept that fact, the entire structure of space-time reveals itself. That's what makes physics so thrilling. Nature doesn't care about our intuitions. She just is what she is. And our job is to listen carefully enough to hear what she's actually saying. All right, here's where we get to the really deep stuff. The speed of light, this number c, isn't really about light at all. Light just happens to travel at that speed. But what c actually represents is something far more fundamental. It's the maximum speed at which cause and effect can propagate through the universe. Let me explain what I mean. Imagine you're here, and I'm way over there, a light year away. You do something, say you flip a switch. Can that action affect me instantly? Can the effect of your switch flip reach me faster than light could travel between us? The answer is no. And here's why that matters. If information, if cause and effect, could travel faster than light, you could construct situations where effects happen before their causes. You could send a message into your own past. Not in some vague science fiction way, but actually, mathematically, according to the rules of relativity. Here's a simplified version. Suppose you could send a signal faster than light because of the way time works for observers in relative motion. Remember, time isn't absolute. One person's simultaneous events aren't simultaneous for someone moving relative to them. If you exploit that, sending faster than light signals back and forth between two moving observers, you can create a situation where a message arrives before it was sent. That's not just weird. That's logically impossible. It breaks causality, the basic principle that causes precede effects. So the universe has a speed limit, and it's not arbitrary. It's the speed at which information influence causality itself can travel. Light travels at that speed because photons are massless. Gravity propagates at that speed. Any massless particle or wave moves at c. But even if light didn't exist, c would still be there, built into the fabric of space-time. Think of it this way. Space-time has a structure, kind of like a highway system, and c is the speed limit on that highway. Not because someone posted a sign, but because of the geometry of the roads themselves. When Einstein worked out special relativity, he found that space and time are connected. They're part of a single four-dimensional thing called space-time. And in that geometry, there's a natural conversion factor between space and time. That conversion factor is c. It's the exchange rate, if you will, between meters and seconds. It tells you how much space corresponds to how much time. And that exchange rate is also the maximum speed at which anything can move, because moving faster would require traveling through space-time in a way that the geometry simply doesn't allow. Here's the kicker. Even if we discovered something tomorrow that moved faster than light, it wouldn't break this rule. It would mean we'd misunderstood what c represents, but there would still be a maximum causal speed built into space-time. The universe needs one. Without it, causality breaks down, and you get logical paradoxes. So when we say nothing can go faster than light, we're really saying the universe has a built-in speed limit for cause and effect. Light just happens to be the most obvious thing that travels at that speed. It's not about photons. It's about the structure of reality itself, about how one event can influence another, about the very notion of past, present, and future. And that speed limit, that's what keeps the universe making sense. So let's bring this all together. We started with a simple question. Why can't anything go faster than light? And what we discovered is that the answer isn't about engineering or energy or building a better rocket. It's about the fundamental architecture of reality. Speed is relative. It always depends on who's measuring. But the speed of light, that's the same for everyone, always. That single, strange fact forced us to rethink everything we thought we knew about space and time. Then we saw that mass isn't constant. It grows as you speed up, making it harder and harder to accelerate. Add energy, and instead of just going faster, you're also getting more massive. The closer you get to the speed of light, the more energy you need, until reaching it would require infinite energy, which means you can't get there, ever. And finally, we realized that c, the speed of light, isn't really about light at all. It's the universe's speed limit for causality itself. It's the maximum rate at which one event can influence another. Without it, cause and effect would break down, and the universe would stop making sense. So the speed of light isn't just a number. It's a boundary condition on reality. It's what holds the fabric of space-time together, and nothing with mass can cross it. Not because we're not clever enough, but because the universe simply doesn't allow it. And I think that's beautiful. The universe has rules, deep rules, and when you follow them carefully, they reveal something profound about how everything works. If you enjoyed exploring this with me, if you love diving into physics with curiosity and clarity without the unnecessary jargon, then subscribe to the channel. We've got so much more to explore together. The universe is full of mysteries, and the best part, we can actually understand them. Thanks for watching. Keep asking questions, and I'll see you in the next one. Hey, thanks so much for sticking with me through all of this. I know some of these ideas are strange. Believe me, they felt strange to the physicists who first discovered them too. But that's what makes it fun, right? The universe doesn't care about our intuitions. It just does what it does. And our job is to pay attention and try to understand it. I hope this made sense. I hope it got you thinking. And if you've got questions or ideas bouncing around in your head now, that's perfect. That's exactly where the best physics comes from. Curiosity and a willingness to sit with weird ideas until they start to click. All right, I'll see you in the next video. Take care.